Assalamualaikum and hi. We are from Group 2. We present about testing and spectrometric characterization of polymers using infrared spectroscopy. Firstly, I will explain about method characterization using IR spectroscopy. Infrared spectroscopy is used to identify polymer structure such as chemical composition and bonding arrangements that resulted from the different IR absorption of chemical bonds such as vibrational transition of polymers upon irradiation of IR. The vibrational transition can be expressed by the equation below, where V is stretching frequency and the unit is per cm. C is the velocity of light, and the mx and my is the masses of two atoms involved in the stretching, and k is the force constant. Particular types of bonds of organic molecule usually stretch within certain rather narrow frequency ranges, which are very useful to determine the chemical structures of molecule. This can be seen using carbonyl group that these groups stretch within range of 1700 to 1025 per cm. The chemical structures of unknown polymers can be recognized mostly through their specific IR absorption frequency. However, the exact chemical structures cannot be deduced from IR spectra only, unless they can be compared with known data or from the IR spectra of their monomers.
Now, let's proceed to the second part, which is method work. As you can see here, for the first diagram, this one is the example of a spectrometer for IR spectroscopy that's called FTIR 6323 spectrometer from Jason. And for the next diagram, this one is the simple diagram on how the IR spectrometer function. First and foremost, we have to rinse a solid sample with a substance like potassium bromide, which it is as an ionic compound that does not show up in IR spectroscopy. It will place it in a special device to allow the sensor to shine through it. Sometimes we will mix the solid samples with solvents like mineral oil that gives us limited and known reading in IR printout. To use the liquid method, we have to involve to placing a sample between two plates of pressed salt, which NaCl sodium chloride, to allow the infrared light to shine through it. After we put the sample into the spectrometer, the infrared light or radiation hits a molecule. When infrared light or radiation hits a molecule, the bonds in the molecule will absorb the energy of the infrared and respond by vibrating. Commonly, scientists will call it in different types, which vibration bending, stretching, rocking, or scissoring. The IR spectrometer has a source, an optical system, a detector, and an amplifier. For the first one, the source will give off infrared rays. Next, it will go through the optical system and move these rays in the correct direction. The detector will observe changes in the infrared radiation. Last but not least, the amplifier will improve the detector signal. Sometimes, spectrometers use single beams of infrared and then split them into component wavelengths. Other designs use two separate beams and use the difference between those beams after one has passed through the sample to give information about the sample. The old-fashioned spectrometers amplify the signal optically, and the modern spectrometers use electronic amplification for the same purpose. We know that infrared spectroscopy identifies molecules based on their functional groups. The chemists using IR spectroscopy use a table or chart to identify these groups. Each functional group has a different wave number that listed in inverse centimeters and a typical appearance, mostly that we can see or that we can observe during the experiment is the stretch of an OH group, such as water or alcohol, that occupies a very wide peak with a wave number near 3500. We also have the carboxylic acid at the range of wave number of 2500 to 3000. For the nitrous is 2300. For alkynes, 2200. Not to forget the carbonyl region at the range of 1660 to 1840. For the conjugation, we have to -20, and also we have the conjugated ketones at 1690.
First example is going to be polymer identification using mid-infrared spectroscopy. And for this example, the spectrometer used is going to be from Perkin-Elmer, which is called Spectrum2 FT-IR spectrometer, as shown in the top right corner of this slide. For this purpose, the sample chosen is polystyrene, and the sampling technique used is film casting. In the middle of this slide shows the structure of polystyrene repeating unit. In order to know what is film casting sampling technique, let's go into the procedures. First is 2 gram of the sample was dissolved in 10 ml of xylene, and then followed by an IR crystal window is placed on top of a paper towel on a hot plate that is set at 40 degrees Celsius. About 2 to 3 drops of the sample solution that has been prepared earlier was placed on top of the crystal window, and then let the solvent in the sample to evaporate, which will leave a thin film of the sample. The crystal window that have thin film of sample on top of it was then placed inside the spectrometer in order to generate an IR spectrum. The transmission spectrum, as shown in the diagram, shows a spike at frequency of 3100 cm-1 that confirms the presence of aromatic ring, and also at frequency 2900 cm-1 shows the presence of CH alkene. There are few advantages and also disadvantages of using film casting technique in order to prepare the sample to use the same spectrometer from Perkin-Elmer. Advantages includes simple, cost-effective, and also it can produce good quality of spectrum. However, this technique is only applicable for soluble polymers because the polymers need to be dissolved in a solvent first, and then it is also time-consuming in order to wait for the solvent to evaporate from the sample. The picture in this slide shows the IR spectra of several other common polymers other than polystyrene, which includes polyethylene, polypropylene, and also polytetrafluoroethylene. In polyethylene and polypropylene, there are CH stretch region around 2950 cm-1. However, differences can be seen between them two because there are differing ratios of CH2 and CH3 groups. While the bottom one, which is the PTFE, have no CH stretch at all because there are no CH groups present in the polymer. So the very weak bands present must be due to the impurities or maybe surface contamination.
Example 4. Application of infrared spectroscopy for functional compound evaluation in olive oil. Many instrumental analytical methods has been developed for the determination of functional compounds in olive oil, mainly mass spectrometry and chromatography. However, these methods are expensive, time-consuming, and non-environmentally friendly. Near-infrared spectroscopy and mid-infrared spectroscopy, coupled with chemometric data analysis, has shown considerable potential for the determination of functional compounds present in olive oil. infrared spectroscopy method has been successfully employed as rapid, non-destructive, real-time techniques capable of on or offline monitoring various quality parameters of olive oil. The advantages of this method is minimum sample preparation, good measurement accuracy with less or no waste generation. Sample is placed in between two transmittive plates and the transmitted intensity in the infrared region is recorded as a function of wavelength. Based on the diagram shown, the most prominent signature at 1745 cm -1 is the characteristic CO stretching vibration, which can be assigned to the fatty acids and ester groups. Being the main constituent of olive oil, fatty acids and their triglycerides dominate the spectra of olive oil.